There are many words in physics that are used in everyday language, and momentum is one of them. But momentum has a very strict definition in physics, and it's defined mathematically. In fact, momentum of an object when the object is going in a straight line, or otherwise known as linear momentum, is defined as follows. It's defined as the object's mass, m, multiplied by the object's velocity, v. So effectively, the more mass an object has, or the faster it's going, the more momentum it has. So as an equation, we have this. We have P is equal to mv. Now, we can't call momentum m because we've already got m, so we give it the symbol P. So P is the symbol for momentum. And obviously the m is mass and the v is velocity. In terms of units, the units are kilogram meters per second. So you can either write it like that, or you can write it kgm/s, where the slash s, 1 over s, is equal to s to the minus 1. Those two are equivalent. And it's also a vector, because velocity is a vector, that means momentum is a vector as well. And because it's a vector, and particularly with momentum problems, the direction of motion of the object, the direction of the momentum is very important, because particularly when you've got two objects travelling in opposite directions, the signs of the momentum will be opposite. One of them will be positive and one of them will be negative. So it's important to look after the signs. So we're just going to have a look at these two questions to demonstrate the importance of the signs and show you how to use this equation here. So here's the first question. We have two identical cars moving towards each other. Both have a mass of 1,500 kilograms. Car A moves to the right with a speed of 20 meters per second, and car B moves to the left with a speed of 25 meters per second. And what it's asking us to do is to calculate the individual momentum of each car and the total momentum of the two cars added together. So we can break this down into two parts. We can have car A and car B. So the momentum of car A is equal to its mass times its velocity, which is 1,500 kilograms times 20 meters per second. That's going to give us a momentum of 30,000 kilogram meters per second. But when we come to car B is moving in the opposite direction. So at this point, it's really important to actually specify the direction of our signs. Now, implicitly, we've used plus 20 meters per second for the velocity of car A. So what we've said there is this object going to the right is going to have a positive velocity and therefore a positive momentum. So we need to say that anything moving to the left, or any vector pointing to the left, must be negative. So with car B, we have to say, because it's moving to the left with a speed of 25, its velocity is going to be minus 25 meters per second. So now, with that knowledge, we can do this one, which is the same mass, and we have to multiply it by minus 25 meters per second. And that's going to give us minus 37,500 kilogram meters per second. So those are the two individual momentum of each car, and the total is going to be the sum of those. So the total momentum is going to be the momentum of car A plus the momentum of car B, which is going to be 30,000 plus minus 37,500. So we're going to end up taking them away from each other, and we're going to end up with a total momentum of minus 7,500 kilograms meters per second, which sounds counterintuitive. The total would be quite a small and negative number, but it just means almost like the balance of the momentum is towards the car moving to the left, because it has a higher velocity and the same mass. So that's how you would look at a question like that. Here in question B, we have an object which is going to rebound, and it's going to go in the opposite direction. So with ones like this, and with part A, to be honest, it's quite useful to draw a little diagram. So here's our wall, here's our ball. The ball is 0.2 kilograms, whichever way it's going, and as it comes in, it's travelling at a speed of 15 meters per second. And then as it comes out again, it's going to be travelling at a speed of 11 meters per second. But those two speeds are in the opposite direction. So we need to specify which one's positive and which one's negative. So again, we're going to use the same convention. We're going to say that vectors pointing to the right are positive and vectors pointing to the left are negative, which makes this minus 11 meters per second. The question asks for the change in the ball's momentum. So we want delta P. And delta P, just like delta V with velocity, is equal to the final momentum minus the initial momentum. Always final minus initial. So we need to work out what the momentum of the ball was after it hit the wall and the momentum of the ball before it hit the wall. So I'm going to do those separately, although you could put those straight into this first line, but I'm going to do them separately just so it's step by step. So the final momentum is going to be 0.2 kilograms multiplied by our final speed, which is minus 11, which is going to be minus 2.2 kilograms meters per second. And then the initial momentum is going to be the same mass, 0.2 times 15 meters per second, which is going to give us 3 kilograms meters per second. So that's the final and the initial momentum. And then the change in momentum, which is the final minus the initial, which is effectively mv minus mu, in sort of the language of motion, final velocity minus initial velocity, v minus u multiplied by m. So the change in momentum is going to be equal to our final momentum, which is minus 2.2 minus our initial momentum, which is 3, which is going to give us minus 5.2 kilogram meters per second. And here we see again that we get a slightly, possibly counterintuitive result, because the change in momentum is larger than either the final or the initial momentum, but because we're taking a number away from a negative number, because of the change in direction, we end up with quite a large negative number.